Hello there, it's Luke, and in this tutorial we're going to be looking at how the autonomic nervous system, and specifically something called the baroreceptor reflex, responds to low blood pressure, whether that's caused by hypovolemia or any other cause that might lead somebody to be in a shock state. Okay, now we've previously discussed and sort of introduced these terms, including cardiac output, which is, just to recap, is the volume of blood ejected from the left ventricle within a minute, and that's related to the stroke volume, which is the volume of blood ejected with each contraction, times the heart rate, and then how that cardiac output times the systemic vascular resistance, which is how we refer to the sort of muscle tone being sort of constricted within the smooth muscle of all the blood vessels, and how those two things combine to improve blood pressure, and in doing so hopefully improve blood flow and perfusion of the tissues of the organs, so that they can undertake normal metabolic process. And we can combine those two relationships into this one sort of statement here, where we're saying that the blood pressure may go up and down depending upon the stroke volume, the heart rate, and the systemic vascular resistance. And we'll look at how the baroreceptor reflex influences those different variables to improve the blood pressure and hopefully tissue perfusion. Now, when we talk about the baroreceptor reflex, we're talking about sort of messaging, nervous messaging, that is occurring between receptors within the arch of the aorta, the carotid sinus, going to the brainstem, and then impulses travelling back down to effector organs such as the heart and the blood vessels. And we can see from this helpful diagram here that you have these baroreceptors or stretch receptors within the arch of the aorta, the carotid sinus, which is actually up here underneath your jaw somewhere, and they relay that information to the brainstem, which then has output to the effector organs. And the part of the brainstem that we're concerned with is the medulla oblongata. Now, it's important to note at this point that that's not the only, the sensory input from those baroreceptors aren't the only input that the medulla oblongata is receiving. It's also receiving information from the cortex itself and other sensors sort of around the body and within the brain itself. So what happens is you have these stretch receptors within the aorta, within the carotid sinus, and they are all the time sending action potential messages and impulses, afferent action potentials, towards the central nervous system. So things travelling towards the central nervous system of the brain and the spinal cord, and these afferent impulses, and they're travelling up these carotid sinus nerves, which joins the glossopharyngeal nerve, and the aortic nerve, which joins with the vagus nerve. And then this is sort of processed within the central nervous system, and there's an efferent impulse back towards the peripheries, towards these effector organs and tissues. So the first thing to say is that the action potential, so these messages that are travelling from the receptors towards the central nervous system, those impulses don't get stronger or weaker. The messages are more or less frequent, and that's how the information is conveyed. So where there's a high blood pressure and the walls of the aorta and in the carotid sinus are very stretched, we're more frequently seeing messages travelling towards the central nervous system. And similarly, if somebody is hypovolemic or they have a poor cardiac output for whatever other reason, they have a low blood pressure, there's less stretch on those receptors, and so it's less frequently sending messages towards the central nervous system. Now, once those messages have gone up to the brainstem, to the medulla oblongata, it can then moderate and send a response to the various sort of effector organisms through their sort of efferent nervous impulses. And one of those mechanisms is to use the vagus nerve, which travels from the medulla and down towards the down towards the heart itself, towards the SA node and the conductive tissue within the heart. And depending on how frequently the impulses are travelling along the vagus nerve, it sort of will slow or raise the heart rate. Now, we might think of the vagus nerve as acting like a brake on the SA node and the conducting system of the heart. So the more frequent the impulses from the central nervous system along the vagus nerve to the SA node and the conducting system, the more frequent those impulses, the more pressure is applied to the brake, and actually the slower the heart goes. And we can sum that up here with this slide. So the greater the frequency of those efferent impulses along the vagus nerve, the slower the heart rate goes. Conversely, if we have fewer impulses travelling along the vagus nerve, the heart rate has that brake released and the heart can go faster. So we're going to consider a situation whereby our person has a low blood pressure, maybe because they're hypovolemic, and so there are fewer afferent impulses to say that there's stretch and give information about the blood pressure to the central nervous system, and consequently there are fewer impulses travelling along the vagus nerve, and so the heart rate will increase. Now, what happens at the same time as this is that there are more frequent sympathetic efferent impulses along a number of nerves, which will affect very different changes, opposing changes within the effector organs. And so if we think first of the heart, there is greater frequency of impulses along the cardiac nerve, which will mean that the heart rate speeds up, but also the contractility, so that force of contraction within the ventricles will increase. And of course, both of these things will increase the cardiac output and hopefully the blood pressure. There's also an increase in sympathetic messages along the sort of peripheral nervous system to the actual blood vessels, the arterioles themselves, which causes the smooth muscle within those arterioles to contract, which will increase systemic vascular resistance by that vasoconstriction, and in doing so, blood will be moved from capacitance vessels and from the peripheries and other tissues, and it will increase the venous return back to the heart, and in doing so increase the preload, which is the degree to which the left ventricle is filled and is stretched, and the degree to which the sort of contractility, so the more force the heart can generate by how stretched it is by the blood that's returning to it. And finally, the other sort of output that the central nervous system conveys along those peripheral nerves is to the adrenal glands, so along the splanchnic nerves in particular, which go to the adrenal glands, and this causes the release of noradrenaline and adrenaline from those specialized chromaffin cells. And of course we know that noradrenaline and adrenaline will interact with adrenoreceptors, and that will occur within the heart. There's beta-2 adrenoreceptors in the heart, which will cause an increase in contractility, so stronger force of contraction of the blood from the left ventricle, and also the alpha-1 adrenoreceptors, which are found in the smooth muscle of all the blood vessels, which cause them again to constrict, and so we're improving the blood pressure, improving the venous return and preload and cardiac output and blood pressure via those mechanisms as well. So we might say that the baroreceptor reflex improves the stroke volume by increasing the preload due to peripheral vasoconstriction. It'll also increase the contractility by direct sympathetic stimulation of the myocardium, but also because it increases the circulating catecholamines, so those adrenaline and noradrenaline which have been released from the adrenal gland under stimulation from the autonomic nervous system. The heart rate is increased because we've released that vagus nerve brake that was slowing down the heart rate. And finally, the systemic vascular resistance increases to increase the blood pressure because of direct nervous stimulation and also from stimulation from the circulating adrenaline and noradrenaline, which have been released from the adrenal glands as a consequence of being stimulated by those sort of efferent nerve impulses. And we can see that all those three things combined, the stroke volume, the heart rate, and systemic vascular resistance, will improve the blood pressure. So in summary, we've revised how the baroreceptor reflex compensatory mechanisms support blood pressure. We've said that the efferent parasympathetic impulses travel along the vagus nerve to moderate the SA node firing and the heart rate, and that vasoconstriction is mediated by efferent sympathetic stimulation from both nervous impulses and adrenal gland release of noradrenaline and adrenaline. Thank you very much.